talk about Gauss's law, it's important to note that when deriving something in E&M, you can always begin from Gauss's law as a first principle. Now, so Gauss's law has two parts. So there's an equal sign in the middle. And yesterday I was talking about the flux side. So the way I write this, you're not going to like because it's all Greek letters. That's the side I was starting to hint at yesterday. And this refers to electric flux, which I wrote like this. The left side, I just put QENC. Which means charge enclosed. This is Gauss's law, written with the symbol for flux. In this class, we will also often say, if we're going to start something with Gauss's law, we'll often just write it with the integral in place. So either one of these can be considered Gauss's law. One is using the symbol for flux, one is not. Now, Q enclosed is pretty simple. It's just all of the charge enclosed. That's all it means. So my example at the beginning, the candle was the charge enclosed because it was inside a surface. This part is the complicated part and the part that each piece needs to be defined. So let me just talk about flux for just a minute because that's that part, the flux portion. And I'm going to kind of space these out. So we can kind of break it up into pieces. And I'm going to go from right to left. This represents a piece of area. This is an electric field. Or maybe a field line. The arrow. This is the angle between the electric field line and the area. So it's a summation symbol, and one of the important differences in this summation symbol is that little circle in the middle. That little circle isn't a big deal. It's something that is being communicated to you, that you are summing up over something that is closed and bounded. Meaning, you can't just, I would not be able to use Gauss's law with this surface, because this surface doesn't enclose a volume. It's just a two-dimensional loop. In order for Gauss's law to be a law, you have to add up the entire area in a closed and bounded surface. So your Gaussian surface, which is what we call the area that we use here, the Gaussian surface has to be a complete enclosed volume, or it's not, or it doesn't fit the law. So you can have a flux that is just of a small piece of a surface and just say this is how much electric flux there is. But to be Gauss's law, it says that if you add up all of the flux over a closed and bounded surface, it will equal the total amount of charge enclosed. That's what the law says. The law is saying if I do all of that, add up all of the flux to a closed and bound surface, it will equal how much charge is enclosed in the surface. Of course, that leaves out one thing, right? This guy, this is just a constant of proportionality. It converts the units of flux into coulombs. It's a constant of proportionality. It's called the permittivity constant. It's 8.85 times 10 to the negative 12th meters squared per Newton squared, meter squared per Newton Coulomb squared. There it is. The permittivity constant. The symbol that I'm using here is a lowercase epsilon, which I'm spelling wrong, epsilon. And epsilon in your textbook tends to look like that. I write it like that, but you guys know I love doing this, so why quit now? So when you write epsilon, it should be lowercase. It should look like that. So compared to like an N or a K. So I kind of give you an idea of what its size should be. So as you write it, that's what it should look like. I'm getting a little bit off task, not as much as you might think. The circle that's there is important because it means the permittivity constant of free space or of a vacuum. When we talk about the natural constants, you learned, I think, only one last year, big G, right? The gravitational constant. So far this year, we've talked about K, Coulomb's constant, and I'm about to show you that it's not a real constant of nature. Epsilon naught, a real constant of nature, meaning it is based on something that is a part of nature. It's not based on something that we constructed. It's something about space. It's something about nature. There's a few others, something that we'll talk about later, the permeability constant will show up later. And there's only 2 or 3 other constants in nature that have a true natural construct. Pi is one of them, E is another. These constants are interesting. These all have units associated with them because their size, the number that is there, is based on the units you choose to express them in. Of course, these don't have units because they're natural constants that are formed because of some kind of proportional ratio in the universe. Pi, of course, shows up because of the ratio between the diameter and the circumference of a circle, and the finding that it's always the same regardless of the size of the circle. E shows up because the proportion of the way in which there's exponential growth. If you look at exponential growth, this number shows up as a proportionality constant. It's without units. The other ones have meanings themselves. This one, the one we're talking about right now, is how well an electric field can be established in free space. The permittivity constant is part of Gauss's law, and you can kind of see that. It's saying something about if you have this much charge, this is how big your electric field will be. Can you kind of see that equality there in the equation? At the same time, this one, which we'll learn second semester, is how well a magnetic field can be established in free space. What's funny is I didn't put lowercase c as a list of the constants here. Do you guys know what lowercase c stands for? The speed of light. The reason I didn't put it up here is because the speed of light is predicted completely by these two. You can predict how fast light passes through space by just using these. It's 1 over the square root of their product. Will give you the speed of light in space. And the really weird thing is pi is in this one. There's just some interesting circular logic about all of these things. that I think is, again, only a handful of you will come to appreciate it, but those of you who will probably go on to do something with this in the future. Because there's a certain appreciation here that I think you have to understand the bigger picture. What we're seeing right here is why and how every antenna on the planet works. There are 7 antennas probably in your cell phone right now. This is how they work and why they're shaped the way they are, why they're placed inside your phone, where they're placed. It can be completely predicted from this relationship alone. Now, I'd love to say it's that simple, but it's not, of course. Anybody who goes into antenna design is destined to make big money, except you are likely to sign, in this country, an NDA that'll mean that you actually don't own any of the things you develop, the company that you work for does, and you won't make much money from it, but you'll probably live a comfortable life. Antenna design is amazing. You guys tend to want smaller, better, faster phones. All of that's based on antenna design. And the antennas in your phone have to be packed in such a way that they don't extend outside of the device, right? We don't want an antenna outside the phone. You understand that that's not the way phones used to be made. You used to have to pull out the antenna and then put it to your ear. And they've now been able to bake it all into that little box. It's kind of exceptional. So antenna design is pretty amazing. So we're going to talk about how Gauss's law is meant to be used. We will use Gauss's law almost exclusively to find out the size of an electric field. That is the way we will almost always use Gauss's law. It can be used in lots of other ways. Clearly, it can be used to figure out how much charge is enclosed. And there is a use case for that we'll talk about. But for the most part, we're going to use Gauss's law to find electric fields, the same way we used Coulomb's law to find electric fields. In fact, this is the first thing we're going to do. I'm going to show you how Gauss's law is to be used. It's a series of steps. I would encourage you to write the steps down. We're on club schedule today, correct? Yes. Which means I have how many minutes? 13. Okay. Let's do this for the simplest example I can think of, a single point charge in space. Okay? Now, in order to use Gauss's law, you have to remember that Gauss's law has both sides, the Q enclosed and the flux. So let's say that my point charge has charge Q and exists in free space where there are no other charges in this vicinity. All right? Step 1. The first step is you need to consider a shape that could be wrapped around your charge to enclose all or a part of it. Now, when I make this statement, the shape we're talking about, I will always refer to as a Gaussian surface. And that's how it will be referred to in your homework and on tests. And in nature, we talk about this shape as a Gaussian surface. The shape is fictitious. It's our imagination. We are using this shape in the calculation alone. But the shape itself shouldn't ultimately matter in the end, because we're just using it to sum up the flux. So no matter what shape we use, we should always get the same flux. When choosing an area, we want to choose an area that is most successful for us. So we want to exploit symmetry and simplify the mathematics. So the first shape I'm going to use is a shape that I think is the wrong one to use. And you'll see why I think right away. So I want to exploit symmetry and simplify mathematics. So I'm going to choose a shape I know will not work. And I'm doing this so that we can understand what we're looking for when it comes to symmetry. Oh, not that. I'll choose a square because it's symmetrical. And I'll put it asymmetrically around my charge. Now, it's not a square. I have to imagine it's a cube. But for the purpose of this drawing, we're just going to look at the square portions of it, okay? We already know from past experience that the electric field coming out of Q comes out like this. So for these 4 lines that I've drawn, it looks like the electric field is perpendicular to the surface. That's kind of nice, right? I'm sorry, not perpendicular. The electric field pierces the surface in a perpendicular way. And in the onset, that might look like a good thing for us. But what about this electric field line, and this electric field line, and this electric field line? We have to add up all of them. Is it kind of clear to you that every one of those electric field lines is going to be exiting the surface at a different angle? That's going to make this sum pretty hard to do, isn't it? Because every single piece of area will have a different angle to deal with. And isn't it also going to be a problem that every single piece of area is a different distance away? Because we know that the electric field is getting weaker as it gets further away. That's not exploiting symmetry and not choosing an area that simplifies things. I think most of you would realize that if I wanted to exploit the symmetry sum, it would be better if I took my surface and maybe placed it equidistant from the charge, right? Wouldn't that exploit the symmetry better? I would have symmetrical surfaces now. Wouldn't every one of the surfaces now have the same amount of flux passing through it? Because the shape is centrally located. But did I solve the simplification problem? Did I make the angles something easy to work with? No. What shape would probably be better? Circle. A circle, yeah. So, okay, a sphere. You're right, a sphere. Thank you, sphere. Gosh darn it. So now let's consider a sphere. Now, obviously, no, right? This is not exploiting the symmetry of the system. Even though it's a sphere, haven't I just increased asymmetry of the system and made the math just as complicated? So I want not just a sphere, but I want to place a sphere so that it is located in such a way that it is central and the charge is at the center. Does that make sense? Now, we know a few things. This is why we had to have Coulomb's law first. Every piece of my Gaussian surface is going to be the same distance away from my charge. Because we've worked with Coulomb's law before, is it clear that it's probably safe to say that the electric field here will be the same size as the electric field here? Is that fair to say? Okay, so the first thing I want you to kind of notice is that the electric field should be a constant everywhere around this surface because we have exploited the symmetry and we have simplified the math. Does that all make sense? All right. That multiplication in the middle isn't multiplication. You guys from mechanics know what it means. What's that product called? It is the dot product. And the dot product requires that we take a look at the cosine of the angle between the area and the electric field. So I will rewrite this. Okay? Now, I've stripped away the bar on top of the E and the bar on top of the A and put the cosine in because that's the one we need to look at. And let's just kind of zoom in here for just a minute. The direction of the area at this point has to be perpendicular to the surface, which has to be a normal to the surface, which is going to have to lie in that direction. That has to be the direction of dA, right? It's pointing away from the enclosure, and it's normal to the surface. Can you see that symmetrically that will be true everywhere? So we have not just simplified the math, but we have also stated or made it so that our Gaussian surface always has a cosine of 0 between the electric field and our area. Yeah?
Wait, so the direction of the area coming off the circle is the same direction as the electric field? That's why the cosine is 0?
Yeah.
Okay. Gotcha.
So do you guys follow that so far? We okay? So that means for every piece of area, the cosine will be 0 and the electric field will be the same size. I'm saying that purposely because what we're really looking to do is try and come up with either E being constant over the surface, or the flux being 0 over the surface. That's our goal, is try and make it so that either the electric field is in line with our area and constant over that surface, or we want to make it so that the flux is 0. That's how we choose a good Gaussian surface. Now, after this, we just execute the integral. And this part is ridiculously simple if you've done the Gaussian surface right. On your test over this, I just want you to know the problem will ask for you to draw in an appropriate Gaussian surface and then use Gauss's law to find the electric field. You will have to choose a Gaussian surface that works. I will show you every permutation of that because there's 3. That's not hard for me to do. Do you follow what I'm saying? There's 3 different ways to do this. You're looking at way 1 using a spherical surface. And we'll look at way 2, 3, and then we'll be done because there's only 3 ways that we can really do this. There's only a couple of symmetrical surfaces that work for our charge configurations. So we're going to execute the integral. So I'm going to slide all this over here, and I'm going to write this out as Q equals epsilon naught times the sum of E times dA times cosine 0 degrees. Now, the cosine of 0 is the same for every single dA, right? It's a constant. And the electric field is the same size for every single dA. We chose it so by symmetry. So the very next step is we can factor out the constants from my integral. All okay? So now I need to add up the entire area of a sphere. That's all I have to do here. What is the entire area of a sphere? That's the volume. Volume is 4/3 pi r cubed. So surface area, 4 pi squared. That's right. Surface area is 4 pi squared. So that's it. We just replace this with 4 pi r squared. That is, we're adding up an area, and the area of a sphere is 4 pi r squared. Now, we were trying to find the electric field. Can you guys solve that for E? I'm hoping. So I solve it for E, and I'm going to get Q divided by 4 pi epsilon naught r squared. I don't know if you see what I'm hoping you'll see, so let me kind of direct your attention. I'm directing your attention. I've separated out the constants from things that are less constant. And just so you know, if you replace 1 over 4 pi epsilon naught with K, do you see what you get? Okay, so Gauss's law supersedes Coulomb's law. It predicts Coulomb's law for a point charge and every other charge configuration. This is what Coulomb's constant actually is.